All right, 2.4. It kind of seems like we're switching gears, but we're not really. We just have to learn about this thing called a complex number so that we can solve more types of equations that have squares in them, right, for our quadratic equations. So some of you may have already heard of an imaginary number. If not, this will be your first time we talk about that. So if you had to solve for x for this something simple like this, x squared equals 16, you know you would take the square root of both sides, and you would end up with x equals, things blurring up, you would end up with x equals positive or negative 4, right? Because if I take negative 4 times negative 4, I get 16, or if I take positive 4 times positive 4, I also get 16. Well, let's try that over here. X squared equals negative 9. Take the square root of both sides. I get x equals, well, I get x equals the square root of negative 9. So I'm stuck with the same thing, right? It's not really an answer yet. Could I do this? Right, I'm going to break it up in there. Now I can take the 9 out. So the square root of 9 is 3, and I'm still left with the root of negative 1. So this is the solution to the system, but I can write this as x equals 3i. Why? Because I is an imaginary number that's equal to the square root of negative 1. So it's an imaginary number in the sense that mathematicians know it's not a real number, and so they've denoted it as the lowercase level I to talk about it. And that's because there are cases where you can get rid of that and actually make, when you perform operations on complex numbers, you can make real numbers. So let's keep going. So here's the definition down here. Been covering it up. Imaginary numbers, right? So I is equal to the square root of negative 1, like I said up here, which then means I squared is going to be equal to the root of negative 1 times the root of negative 1, so therefore it's equal to negative 1, right? And that's how we can use it to do operations with complex numbers that will actually give us real numbers as an outcome, right? So if we know I is equal to root negative 1 and I squared is equal to negative 1, there's this thing called complex numbers. So this is kind of the standard way you're going to show a solution that has an imaginary number in it. It's going to be a, which is some number a, plus some other number b times I. So these are some examples. Negative 6 plus 4i, that's a complex number. It includes both a real and imaginary part. 7 minus I root 2. Yep. And even 0.5 times I is a complex number because a is just 0, right? So plus 0. So these are different examples of complex numbers. So we are going to be working with operations with these and simplifying them. So it gets kind of fun. It's like back to solving equation days. So here's our first example where we're going to add 4 minus 7i, that's a complex number, plus negative 11 plus 9i, that's a second complex number. Well, let's just take the parentheses out of this thing. This becomes minus 11, and that becomes plus 9i. Okay, what can I combine? Well, I can combine this and this, right? They've both got i's in them, and then I can combine my regular plain numbers. So 4 minus 11 is minus 7, right? And then now let's combine my i's. Sorry, minus 7i plus 9i is plus 2i. So do I have it in my complex number form, in the form of a plus bi? Yes, so that's the solution. I didn't even need all this space. Okay, what about if you have to multiply? Okay, this one is, you're going to use the FOIL method, or the same way we were for factoring, right? First times the first. 6 times 2 is 12. 6 times negative 5i is negative 30i. 8i times 2 is plus 16i. 8i times minus 5i is minus 40i squared, right? Because I have two i's there. So now when I'm simplifying this, what do I have? I have 12. Minus 30 plus 16 is minus 14i. And then, oh, I realize this is supposed to be a different, I was like, why is my answer not matching the book? Because this was supposed to be a subtraction. We're going to multiply. And then we have here minus 40i squared. Now, we know what I squared is equal to. I squared is equal to -1. So I can plug in -1. So this becomes 12 minus 14i minus 40 times -1. So I have 12 minus 14i plus 40. Okay, 12 plus 40 is 52 minus 14i. Now it's in the standard form of a plus bi, complex number. So that's the answer to that. So we're going to do a couple more multiplication ones. You can pause, try them, and then come back and see if you got the correct answer, right? This one we're just going to distribute. Negative 2.5i times 8. Well, 2.5 times 8 ends up being 20, I think. I'm just going to check. 50. Why did I say that? Oh, I put times 20. My brain isn't working. I've been making a lot of videos today. 20. Yes, negative 20i, right? Okay, and then 2.5 times 9. Well, that's going to be a positive. 22.5. But I have two i's here, so this is I squared. So same case as above. Now I can plug in -1 for I squared, which comes out to be, I'm going to write it in this a plus bi form. So I end up with negative 22.5 minus 20i. And there's my solution. All right, what about this one? We've got 3 minus 2i and 3 plus 2i. 3 times 3 is 9. 3 times 2i is plus 6i. Negative 2i plus, that's minus 6i. And then this is minus 4i squared. So we can see right away that middle term is going away. So I end up with this, which then I can substitute in my -1 for I. So that's 9 plus 4. So the answer to this is just 13. So what do you notice? If I have an expression 3 minus 2i and the other one is the same but has a plus there, I end up with a real number. This is what's called a conjugate. And it's called a complex conjugate because it has the complex number, right? And we use the conjugate to help us simplify equations, which I'm going to show you in the next one. Our last example. So here's that definition of a complex conjugate where the products are a real number. So it helps us a lot when we have these quotients and we're trying to get rid of denominators. We use that a lot in calculus. So for example, if I have 10 over 2 minus I, they want us to write it in the form of a complex number. So the way we are going to do that is multiply by the complex conjugate, right? So if I have 10 over 2 minus I, what is the conjugate of 2 minus I? It's 2 plus I. So I want to multiply this denominator. I'm going to do this. Times 2 plus I. The problem is whatever I do to the top of this thing, I also have to, or the bottom of this thing, I also have to do to the top, right? So now let's solve this and see if it helps us. That becomes 10 times 2 is 20 plus 10i over 2 times 2 is 4. Then it's plus 2i minus 2i and then minus I squared. Okay. So now I have 20 plus 10i over, the middle terms go away, and I have 4 minus -1, because I squared is -1. So then I have, that's going to be 20 plus 10i over 4 plus 1 is 5. Now I can definitely write that in the form of a plus bi because I can simplify this, right? 20 divided by 5 is 4. 10 divided by 5 is 2. And there we go. That's how the conjugate can help us. You can always use the conjugate too, not with just with i's, sometimes with roots, and it gets rid of that square root for you when you're trying to simplify things, but something for the future. See you guys later.